So good morning and welcome back. Today we'll be concerned with some technical aspects of covariant derivatives on associated vector bundles. And so far we discussed this topic sketchily along the following lines. We started with some principal bundle P with some fiber G, such that there's a right action of G on there. And on this principal bundle total space here, we assume there's given a connection one form omega, because without a connection one form somewhere, there are no covariant derivatives either. And then we considered an associated vector bundle. So that was for some typical fiber F, this total space PF in the way we defined it with some appropriate projection map down to M. And as I showed, the construction of this PF, and in fact the association of such an associated vector bundle, requires the information that is now in some left action. In some left action that takes a group element and acts on the fibers F from the left. And in fact, you need to provide this datum of a left action in order to construct this associated bundle. But once you have provided this left action, then you have here the principal bundle, and here the associated bundle. Now, a connection we saw effects a parallel transport in between the fibers of the principal bundle. So if we look at some picture of this principal bundle with the base space M and the fibers, so a local picture, the fiber G, then this connection one form effected a sense of a parallel transport along a prescribed curve in the base manifold. You get a parallel transport of this element to here, and that was this parallel transport map tau. Now we saw that if we go to the associated bundle, or we argued if we go to the associated bundle, which now has different fibers, so these are the fibers F, so they have a different color. Nevertheless, we can actually use the parallel transport in the principal bundle here in order to effect, again for the same curve in base space, to effect also a parallel transport between the fibers of the associated bundle. And then the idea, so this was the picture so far, so this is the association of the bundle by providing a left action, okay, on the fiber. And the idea of a covariant derivative was then to say, well, let F actually be a vector space. So far, no mention of that was necessary. But now let's say that F is a vector space, and let's correspondingly consider only left actions that are linear. So I should maybe write it like this. If the group acts on F, it acts on F linearly. And because we have this vector space structure, we have an addition and S multiplication, we can actually compare a section, if we now look at a section sigma that takes this point, say, to here, and that takes this point, say, to there, then we can actually take this point, parallel transport it over here along a curve, and compare the difference, because we now have the means by this addition to subtract here. Okay? And then we see this difference, and then we can construct from this difference and how far we traveled here, well, in parameter space and taking derivatives, you know how that works, we can construct a differential quotient, and by that way, in this way we can construct a covariant derivative. So that's the idea of a covariant derivative. It's very geometric, it's very intuitive, and it's technically a disaster. Okay? It's very difficult to implement technically. You can, and what you get is right, but there is a much neater way to do the same thing. And the neater way we're now going to discuss, so at least it's a technically neater way, is the following philosophy. So I again depict the elements in the game. So again, we have the principal bundle. And you see, so this section sigma here, whose covariant derivative we want to construct, that's of course a section here, right? And the construction happens over here in this view so far on the associated vector bundle. The only thing we get from the principal bundle is the parallel transport. We push it over here, okay? But then the construction takes place here. So now the idea is the following. So again, we have the same ingredients. Obviously, we also need a left action. We also need a left action that is linear, which also requires this f, that f is a vector space. So we need to start there. And now, again, we wish to construct a covariant derivative for a section sigma over here. But rather than doing this construction of the covariant derivative on the right-hand side in the associated bundle, we play the following trick. We associate with this sigma a unique function phi sigma that lives on this P and is valued in the F. So on P, we can establish such a function. And I already mentioned the corresponding theorem that, well, there is also a G equivariance condition for this. I'll write it down in a second. But there will be a one-to-one map between sections of an associated bundle and typical fiber F-valued functions on the total space of the principal bundle that throws over this associated bundle. And one has to say that this phi sigma that's constructed from this sigma, one has to say that it is G equivariant. And in this G equivariance sits the information about this left action. So I write this down. And then the point is we will then actually establish or use the exterior covariant derivative that sits here, that we discussed before. We'll apply it to such f-valued functions, and thereby we get a derivative of the function sitting up here. But what we actually want is a derivative of this section down here. Well, this section corresponds to this function one-to-one, and the other way around. Given such a function, you can construct such a section. I'll write down the theorem in a second again. But we still need to push this down here, okay, what we get. And then we also get a covariant derivative down here, and that coincides with what you construct here. So rather, the new view is, rather than constructing things over here in the associated bundle, you immediately construct it on the principal bundle. The only information, well, that makes up the entire associated bundle, namely this left action of G, that goes into this G equivariance here. Okay? But then you can totally forget about the structure of the associated bundle and do everything on the principal bundle. And that's technically, fantastically much more simple. Okay? So what's the key theorem that allows us to do this? And I quoted this theorem before, and I wanted to push the proof to a problem sheet, but then the problem sheet was filled with other important stuff, so we'll do the proof today here. So the key theorem is that if P pi m is a principal bundle, and PFM is an associated bundle via the definition of this left action, then. So if the condition is like this, then there is a bijection or a bijective correspondence between sections sigma of the associated bundle, that is pi f after sigma is id m, and G equivariant functions phi on the principal bundle that are, however, typical fiber f valued, and this is the section property, of course, and the G equivariance property. Okay, what can it be? G equivariance. The phi must be compatible with the G actions in some way. So what can you do? You can write down phi, and it has to act on a point, P. And on a point, we can act from the right, because an element of the fiber bundle, we can act from the right by G. That's the right action that is, well, here I didn't show it anymore, but that is here used or needed in the definition of the principal bundle. Okay, and now we can require that this be phi of P, but the phi is f valued, but on f we have a left action, that's the left action, and require that the inverse of G acting from the left on phi of P is the same as phi of P, where the P is being acted on from the right by the G. Okay? And the statement is, whether I speak about a section here, if I have a section here, I can always construct a G equivariant function up here. If I have a G equivariant function up here, I can always construct a section. And most importantly, if I start with a section, I construct such a function from it. And then from this such constructed function, I reconstruct this guy, I get the same guy back. And the other way around. So there is no information loss in the type of construction we do. There could be constructions that from here you construct something here, here you construct here, but it's not that you can go the whole way around and come back to what you started from. But that's in fact the case. Okay? And because that is the case, it's absolutely equivalent to think of sections of the associated bundle or G equivariant fiber-valued functions, F fiber-valued functions, on the principal bundle. Okay? That's the idea. And that's of fantastic technical use. So let's try to prove this. So let's start with the first direction proof. So assume that we start with a f-valued G equivariant function phi on the principal bundle. We construct from it the following section, sigma, and I write sigma down phi because it's constructed in terms of phi. So it's supposed to be a section, so from M to PF of the associated bundle, and we define it sigma phi of x, so x is a point in M. We define it as P phi of P, where this P is some element of the fiber over the point x, and it's the fiber in the principal bundle because we want to feed this P into the phi. The phi goes from P to M, so we can feed it into there. And this is the equivalence class that defined the elements of the associated bundle. You remember by identifying such pairs if they're equal, if two pairs are equal, if one, the second element can be constructed from this one by a right action of G and the second one from this one by a left action of G inverse. Okay, so that was the definition for the elements here in the associated bundle. Okay, so now this looks like a funny definition because you say you have an X, but on the right-hand side you say this can be any P as long as it's in the fiber over X. It's not clear whether this is well-defined. It could be ill-defined, but in fact it's well-defined. So it's well-defined. It's the first thing to check. Since, well, what do we have to check? Since for any P prime that's in the fiber over X, I could have said for any other P prime in the fiber, we know there exists a unique group element G such that P prime is the P acted upon from the right by the G. It's always the same business in the principal bundle, but then we have that P prime phi of P prime is, of course, P acted upon from the right by G, comma, phi P acted from the right by G. And now we use the G equivariance of phi, because we say we are given a phi, and the assumption is that the phi is G equivariant, so we can use its G equivariance. And that's then, of course, P from the right by G, and then G inverse with the left action, it's the other action, acting on the phi of P. Aha, but this, of course, is because of the definition of these equivalence class brackets. This is, of course, again the same as P comma phi of P. Okay, and that's the same as we wrote here. So it's well defined. Okay? And obviously, if we project back by pi f, okay, pi f selects this one, pi f of this guy is pi of the first entry, but that's x, so you go back. Okay, so since pi f after sigma equals it m, as I just argued, sigma phi is a section of Pf. And that's all we wanted to show. So given a G equivariant function on the principal bundle total space, we construct in this way. There may be other ways, but we use this way, and we'll see this is the way we're going to need. We construct a section on the associated bundle. That's one direction. Okay. Now, now we go the other way. So we first construct the two maps, and in the end we have to show that really no information is lost by going back and forth. So the second direction, B, is given the section sigma, given a section sigma of the associated bundle, construct the phi, but now we call it phi sub sigma because it's a phi that's constructed from the sigma. This ought to be a function, an f-valued function on the principal bundle. And this guy we define phi sigma of a point P of the principal bundle is defined as the inverse of a map IP we met before, but I write it down again, applied to sigma, That's the sigma we start from. The sigma needs to eat an element of M, but this is an element of P. Well, we can use the principal bundle projection P and project it down and plug this in. Okay. So anyway, that's the definition. So now we should think of this I again. So we had a map I. So this is the inverse of it. But we discussed a map I, which is this F goes to the fiber over a point pi of P. Okay? So it looks a little bit like, why do you first do pi and then pi inverse? Well, you know that this inverse is not an inverse, this is the pre-image. So pi of P is a point, but that's the pre-image of the point. So the result is more than pi. It's the entire fiber in which pi lies. P, not P, pi P lies. Okay. Okay, so we have this map, and this map was defined by taking an element F of the fiber and mapping it. So this clearly lies in the principal. No, hang on. Where do I want this to lie? I want this to lie in F. No, this must lie in the I think I want this. Aha. So I want this to go down here with this pi, but I take the pre-image because I want the whole thing to lie in the associated bundle. So what I said before was true, but this is what I want. I go down to the base point of which P in the principal bundle lies, is a point in M, in the manifold M, and then I look at the fiber of the associated bundle over this base point. Okay, this is where I lie. And I associate with this F, I associate the point P, comma F. So that's the IP of F is defined like this. And this is again the bracket that is defined in order to define the points in the associated bundle. Okay? And so I think it was on the second last problem sheet. Yeah. So second last problem sheet. We constructed explicitly the inverse of this I, but in fact I is IP is a bijection. And of course, if you require continuity, it's even a homeo. If you require differentiability, it's even a diffeo. Okay? So this is what the problem sheet said. Okay. Okay. That's the info on this I. So the I inverse really exists. Okay? And we're invoking this I inverse. So is everything fine? Yes. So this takes us to a point in the manifold M, the base manifold. The sigma takes us up to the associated bundle total space, and the I inverse takes us from the associated bundle total space back to F. So this guy is really F valued. That seems to work out. Okay? So that was this thing. So now from the definition of this F here, we derive that if you act, we'll use this in a second, if you calculate this guy, IP, and the P acted upon from the right, G, F, that is of course P acted upon from the right by G, comma, F. And that is the same as, I can now act again from the right by G inverse without changing this if at the same time I act here from the left. Hang on, is this right? Is this what I want? Well, I can do it simpler. This is, I think, wrong in the first place. Okay, this last step was not correct, but this is true. But now I can simply, so this is most straightforward. The other way can also be used, but this is, I can act here from the right, and I can act here from the left. That's just the definition of the bracket that allows us this. And this is then, of course, I, P down G acting on G inverse F. So what I want to say is that this guy is the same as this guy, and we're going to use this in a second. So this is obvious directly from the definition of this bracket. So now let's try to show, so we constructed a phi, and now let's try to show that it's G equivariant. That's the aim, because we start with a section, I say it leads to a G equivariant phi. So show G equivariance of phi sub sigma. Well, so we start with the left-hand side of the equivariance condition, and we try to make our way to the right-hand side of the equivariance condition with the definitions we have. So you see, this is the left-hand side, and we want to arrive here. All right, so let's plug in what we got. So phi sigma of P is this guy. So if I write P acted upon from the right, then I have the I inverse of the P acted upon from the right. This is because I have this and this, okay? Then I let this act on sigma of pi of P, but P is now P acted upon from the right by G, okay? That's just plugging this in. Now the first insight is that if I'm in a principal bundle and act with the G from the right, I do not change the fiber where I am. I stay within the fiber. So this guy is pi of P. Nothing changes in here. Okay, so what's our next step? It's the pi of P. Yes, and the trick is to write now this sigma of pi of P, to write this whole bracket as the phi sigma of P, which it is, right? Yes, that's what this guy is. And, pardon me? No? Yes, no. It's the IP of. Yes, because phi sigma of P is IP inverse of this whole guy. So this is the IP of this. Okay, thank you. Thank you. Yeah. Okay. So what we have in total is IP acted upon from the right inverse after this IP. So, and now we're using this guy I derived before in order to rewrite this. IP of F, we said, is the same as IP acted upon from the right by G of G coming from the left of the F, phi sigma of P. Agree? But now I have I inverse P sub G after IP sub G. Not sub. IP acted upon from the right by G. So this is the identity. So the whole thing is G inverse acting from the left on phi sigma of P. And that's what we wanted. That's the right-hand side of the equivariance condition. So that's correct. There is this equivariance. Okay? Good. So what have we shown so far? We have shown that we provided some construction to go from some section on the associate bundle to some F G equivariant F-valued function on the principal bundle and the other way around. What we haven't shown yet is that by this construction no information is lost. Okay? I mean, I could have, to make the point precise, I could have constructed the zero-valued function up there, which is certainly G equivariant, okay? And I could have constructed the zero section there because I have a vector space. So this would be guys constructed from the other in a sense, but I would of course lose all the information. So the next step is to check whether we can recover the object we started from by going back and forth. So C, check that no information is lost. So how do we check this? Well, we try to construct a section from a F-valued principal bundle function, which in turn, well, section sigma, which in turn has been constructed from a section sigma. Okay? So this is the original section we put in. Yeah? So this is the section we start from. From this we construct this induced function on the principal bundle, and from this we construct this induced section of the associated bundle. We go back and forth, and of course we want to arrive at the original section. And we have to check the other way. We want to construct a principal bundle F-value G equivariant and so on function from a section which has been constructed previously from a principal bundle function phi, and we again wish to show that this recovers the original phi. So so it's this sigma, this blue sigma here, that we recover, and it's the blue phi here that we recover, and the other notation is just the notation. Okay? So let's start with this S bit. So, okay. So let's write down sigma phi sub sigma. Well, it's a sigma. It must start on some x of the manifold M. Well, what's the definition of sigma down some phi? Well, that was defined as the bracket, because it's supposed to map to the associated bundle, of some p, you remember, this was some p that lies in the fiber over x. And that was the fiber in the principal bundle over x. And here we have the phi of the sigma, that's this phi sigma of p. And we check that this is well defined. Okay? But now we have to also replace what this phi sigma was. And the phi sigma at the point P was the IP inverse of the sigma, that's down here, of the pi of the P that's given here. That's this thing. Now, what kind of object is this? Well, this here is an F in the fiber F, because IP inverse goes back to the fiber F, such that I down P of F is exactly sigma of pi of P. Well, that's not such a secret, but that's just the definition. But the IPF was the P with the F bracketed by definition of the IP. So that means this is an F such that PF is sigma pi p? Well, pf, is sigma of pi of p. But pi of p was the p was somewhere in the fiber over x, so this is the sigma of x. For every x in M, we recover the sigma of x. Okay? All right, so the other way around. We have a phi, and we construct it from a sigma that was in turn constructed from a phi. Now the phi is a G-equivariant f-valued function on the principal bundle, so we have to feed it a point P in the principal bundle. The definition of this guy was I sub P, that's this P, inverse of sigma, well, that's this sigma, so it's the sigma phi, of the pi of the P, finished. Now, this is IP inverse of, so what was the sigma sub some phi? The sigma sub some phi was an element in the associated bundle, so it must, or it can be written like this. And it was the one where we took some P in the fiber over this point. Well, I can take this P directly. If I can take some P in the fiber over pi of P, I take the P immediately. Why not? And we know it's well defined. And then over here, we had to take the phi that's given down here of the same P. And that's this thing, okay? So now this entire guy, of course, lies in the fiber F, because this phi is supposed to be F valued, but also this IP inverse lands back in the capital F. So this is an F such that IP of F is this guy, P phi of P. Okay? Again, the same trick, but the IPF is the PF. Okay? So if this is the case, then the F is this guy. But that's the F. So that's the phi of P. Also there. That's it. Okay, so that was the theorem, and that's what we're going to use. So we actually want to talk about sections and covariant derivative of sections in the associated bundle. But the first thing we do if we are handed such a section, we push it up to an f-valued function that's G-equivariant function on the principal bundle. Okay, so we know we can always do this without losing information, so we'll now do this. This is the idea of this approach we're discussing today. Okay, so let's look at so this is finished. Okay. Now let's look in particular at a G-equivariant function, because we know we have to deal with those. We look at such a guy. G-equivariance, we had it before, is P acted upon from the right by G, is G inverse acted upon from the left by this action on the fiber F phi of P. And we'll now derive a simple implication of this, because we can look at the representation of this G group element close to the identity. You know, we can represent them all by this one parameter group where A is some element, some A from the Lie algebra, from the tangent space at the identity. We can write down the equivariance condition, the G equivariance condition, like this, acting from the left on phi of P, because if you go backwards, you get the inverse. Okay? So this is immediate. So what do we want to do with this? Well, we want to look at this, we want to look at the derivative of this. And what we're also going to say now is that we look at linear left actions. That will be important. So now specialize to the left action by G from F to F being linear. And of course, that statement only makes sense if the F is at the same time required to be a vector space. So the theorem we just proved has nothing to do. We didn't use any vector space property of F, but now we're going to use it. So now we specialize to linear action. In particular, if then the group can act on there, the Lie algebra can act also on there. Right? Think of matrix groups. If you have a finite dimensional vector space, so let's say finite dimensional, to tie it down, then of course the group action can be given by a matrix action. Then you know the algebra is also given by matrices of the same type that can still act the same way. That's the trick we're going to use. But now let's take this G equivariance equation and let's derive it. So it's clear that if we take the derivative of, where is it, up here? Okay, the derivative of phi of P from the right, exp at, and we take this derivative at t equals 0, and the right-hand side is d by dt exp minus at, acting from the left on phi of P. Everything fine? Okay. Also at t equals 0. So, what's happening here? Well, here we need a product rule. I'm sorry, a chain rule. Okay. So this yields d phi, because it's a function, it's just the derivative of p evaluated here is simply of p. So this is the position where it is. But then now this is a one form. It's the derivative. The one form eats a vector. Well, it eats, of course, the inner derivative. Tangent vector. Okay. And we know what the derivative of this guy is. It's the vector field on the principal bundle starting from the point where from the point P I move with this function. It's the induced vector field here on the principal bundle. We constructed this before. It's the left-hand side. And the right-hand side, what's that? Well, this guy here is totally independent of the t. So the derivative only acts on here. Okay? So it yields a minus sign, minus a, e to the minus at, but evaluated at t equals 0 is the identity acting on phi of p. Now, this is a Lie algebra element, and actually this is an action of a Lie group on F. But that's what I just said before. Because we now have a vector space and a group action, therefore, on it, because it's linear, we can act with the same matrix here. So it's the same action. I can use the same action. Okay? Aha. But now it's also neat to write this A as the omega of x up A. It's the same x up A as here. And what's the omega? Omega is the connection 1 form. How does the connection 1 form make an appearance here? Well, it makes an appearance because you know that one of its properties is that it takes a vertical vector field and it yields the Lie algebra element that generates it. So we inject it here in order to rewrite this A in terms of omega. And altogether, we get the corollary, and it's the corollary of the equivariance, of the G equivariance of phi, of G equivariance of phi, it's a corollary to that, is that d phi of a vertical vector field xa plus, take this to the other side, omega of xa acting from the left on phi is 0. For a linear left action. Okay? It's a little corollary which will come in very handy in a second. All right, so equipped with this shiny new tool, we can now set about the construction of the covariant derivative of some section sigma that lives here on the associated bundle. So we wish to construct a covariant derivative and this covariant derivative will be denoted by some nabla. So it's this covariant derivative. It eats a vector from the tangent space at some point to the base manifold. That's the whole idea. And it should act on this section. Okay? And what it should produce is it should produce, again, a section of the same bundle. Yeah, a section of the same bundle. So a covariant derivative acts in some direction, t, on the base manifold, on the tangent space to the base manifold, and it makes a section of the bundle into a section of the bundle. So if this is the associated tangent bundle, it's again a vector field. If this is some tensor bundle, it's again a tensor field. That's what you know. Such that, and we have some requirements there, and one is that in this lower index t, it ought to be C infinity of M linear. So if there's some function f that comes from C infinity on M, and T and S are vectors at the same point, shouldn't call this P, should call this rather X, at the same point in the manifold, in the base manifold, then this is F times sub T of sigma plus nabla sub T of sigma. So this is one rule we wish to establish, or we wish to have satisfied by our construction. So this is just formulating what we're aiming at. Then the covariant derivative should be merely additive in the section. So if I have a section sigma and I have a section tau and I add them, I wish this to be the sum of the covariant derivatives of the two. Okay? And the third property we want to require here is that if we act on f times a section, where now the f is again a c infinity m valued function, then this ought to be the direct action of the tangent vector to the base manifold T on f gives a function times sigma plus f times the covariant derivative down sigma. We're not going to require some further Leibniz rule for some tensor products, because that would leave the bundle that cannot be set at this level, but this is what we want, and this is what we're going to need for the quantum mechanics example. Okay, so this is what we wish to construct. Now, this is here. This has nothing to do at first sight, or actually, with this being the associated bundle to some principal bundle on which there is such a connection 1 form. And in fact, these are conditions one writes down if one does some kind of more naive construction of the covariant derivative, and then one finds, oh, you need to provide some gamma coefficients and so on if you want to do this. But now we want to not postulate this as a structure that could live here with these properties. We want to import it from over here, okay? And the first thing we do, we will, of course, not deal with this sigma directly. We'll rather deal with the induced phi down sigma here. And from now on, I will only call it phi. And it is the phi that has, because you actually want to construct covariant derivative of such a section. Whenever I now speak of the phi, I mean the phi that has been constructed from the sigma. Okay. So we proceed in 2 steps. The first thing, so proceed in 2 steps. So the first step is that we define the covariant derivative acting on this phi. Well, that's not such a biggie, because we already defined the covariant derivative even on any k form, and it became a k plus 1 form. Well, this is a 0 form. It's this phi here. This phi is a fiber-valued 0 form on the principal bundle. It's a function. It's a f-valued function. And I think when I introduced the covariant exterior derivative, I had it flower-valued, right? So now flower is f, okay? So, and this was simply defined as the d phi after the horizontal projection of any vector I plug in, okay? That was the definition. So I should just say recall the definition, because we had it before. Now, having made this definition, I make the following claim, and we made a similar claim before, but before we made this claim for the connection 1 form. If the D was acting on the connection 1 form, we had an explicit expression for this. Now it's acting on something different. It's acting on some G invariant 0 form that's f-valued. It's a different thing. So we have to think again. So we have the d phi. It can act on some x. Where does the x live? Well, this is now a 1 form, so the x must clearly be either a vector or a vector field. Let's say a vector, a tangent vector to the principal bundle, because this is a 1 form on the principal bundle, f-valued 1 form. It's clear that the entire guy is f-valued, right? But that's just for information. The claim is that this guy, this is equal to d phi of x, so it's actually the exterior, the covariant exterior derivative is the exterior derivative on x, but with a correction term, and the correction term is omega of x acting on phi. Okay? And this looks very, very similar to what we had before when this was a 1 form. And you see, before for the one form, we had something, I wrote stuff like this, right? Which said it actually acts on here, right, by the adjoint action, whatnot, but it's also a wedge because this was a one form. Well, now there's still a wedge, but it's a wedge between a one form and a zero form. You can also write this as a product, okay? But the wedge extends there. Let's write like this, that's the clearest. But again, in the literature, you will find omega wedge phi. And okay, but let's leave it here. Obviously, we need to prove this. So again, the proof proceeds in two parts. We can decompose this x into a horizontal and a vertical part. And let's say x is vertical. In that case, we can write it as an induced vector field, induced by some Lie algebra element of the group. And then we evaluate the two sides. So we have d phi on x. Well, I just used the definition. This is d phi of hor of x. But x is vertical, so hor is 0. This is d phi of 0. D phi is linear, is 0. That's the left-hand side. Now the right-hand side is d phi of xa plus omega of xa acting on phi. But we just proved before, that was our corollary, that this vanishes. Because of the g, so this is the g equivariance. It's the g equivariance of the phi. Okay, that was this. B is x is horizontal. Well, that's simple, because then d phi of x is simply the little d phi of hor of x, but because x is already horizontal, it's simply the x again. That's the left-hand side. And the right-hand side is omega of horizontal acting on phi. But omega is the connection one form. It's defined to annihilate every horizontal vector. So this is I'm sorry, I forgot. So of course, the entire right-hand side is d phi of x plus. So this is 0, and the d phi x survives, and then the two sides are the same. Okay, left-hand side, right-hand side. Okay, fine. This is proven. This is a fact. So what do we have now? So if we have the d phi of x, this is a kind of a covariant derivative. I mean, for fun, we could write d sub x on phi being d phi of x, okay? And you see, this is linear in the x, C infinity of p linear in x. The phi appears here also linearly, so if you take, well, additively, if you take the sum of two of those guys, that will pull apart. And if you take an f, that will also, it has all these properties, but this is actually, this looks more like a covariant derivative of some function up here. In particular, this tangent vector x here is in TPP. It's a tangent vector up here. But we want a covariant derivative with a tangent vector in the base manifold. I want to go in this direction in the base manifold, not in the principal bundle somewhere. So this can't be it, and hence this is only step one. We proceed in two steps. We constructed, in a sense, we constructed a covariant derivative acting on these functions. Okay? But we want it down here. Well, we do the standard trick. And we localize the whole thing by introducing on our bundle, on our principal bundle now, we introduce a section phi, little phi section. So pi after phi is it m, in order to locally trivialize the bundle, choosing a section phi in the principal bundle, we can pull back. What can we pull back? Well, we can first of all take the big phi function that lives up there, phi that goes from P to F, and which is of course equivalent to our section, right? And we can pull this back to a field, phi, okay, I shouldn't call this phi, I wanted, yeah, okay, good. We can pull this back to a, to phi star of phi, but you know that the pullback of a zero form is simply phi after phi in this case. Okay? And we can also take the omega, right? What is the omega? The omega is a one form on the principal bundle that's Lie algebra valued. We can pull that one back to phi star omega, and we already have a name for this. Phi star omega, we called this the Yang-Mills field. That's the omega. So if we choose a section here, phi, we usually can't choose a global section on a principal bundle, because then the principal bundle would already have to be trivial. So we only choose a local section here, U. Okay, so this would then be the induced Yang-Mills field induced from this choice of section. So this Yang-Mills field is now, of course, a one form on the base manifold, but still Lie algebra valued. We had this before. Okay, so we pull this guy back. And of course, we can also take our covariant, exterior covariant derivative d phi. What is that? That's also a one form on the principal bundle, and it's f valued, right? And we can pull this one back to phi star d phi. And what is that? That is a one form on the base manifold that's f valued. That's good. So we plug in a vector and we get an f. And it's actually this guy, the pullback of the object we just constructed, okay, for which we will define. Well, let me do this in a second. So these are the objects I constructed so far, and they live up there on the total space, and I all pull them down, pull them back by some choice of section. Okay, so let's do this and let's see what happens, and then you'll see in a second that we're done. Then what do we get? Well, we start on the left and finish on the right. So we take the pullback of the d phi, and that we apply. So the d phi was to be applied to a tangent to the principal bundle, but now this needs to be applied to a tangent vector of the base manifold, because it's now a one form down there, an f-valued one form on the base manifold. Okay, so let's look at this expression. What is this? Well, this is obviously the phi star. It's the pullback of the hang on a second. Can push it forward and then pull it back again. Okay, let me see whether we have to be a bit more careful here. No, that's fine, that's fine. So we can do it like this. This formula up here that I wrote with x's, right? D phi of x, d phi plus omega x. This can be written without x's, okay? And it's equally true. So this is then the pullback of d phi plus omega applied to phi. Right, from the corollary up there of t. Now, the pullback is linear, so this is clearly the pullback of d phi of t plus, so now it comes, it's the pullback of the omega applied to phi of t. Now, the pullback and the d, you may remember, they commute in quotation marks. So this is the d of the pullback evaluated at t. Now here we must look a bit more closely. It looks a little funny. How would the pullback act on this operation of the acting? Remember, there are actually two operations at work here. The omega acts on the phi, but there's also a wedge between them. Okay? Now, the wedge here is really a multiplication because this is a function, this is a one form. In any case, that's just a special case of the wedge, and we know that the pullback distributes over the wedge. So this is really phi pullback of omega acting on the t. Wedge, but okay, I write it, wedge phi pullback of the phi. But you can forget about the wedge because this is again a function. This is like more like a product. Okay, but you can write the wedge. There's no harm in writing the wedge. Okay, yeah, but what are these objects? Well, this guy here is the pullback of phi to the base manifold down here. But that is f valued. Let's call this little s. We didn't give it a name before. No, so let's call it little s here. And so this s is ds of t plus this here is the Young-Mills field associated with the connection omega. That's a one form now, a Lie algebra valued one form on the base space. I should have put the action symbol in any case. Now it acts from the left on this guy. Well, this is again this S field on the base space, a local. No, it's a local SF valued function. So this so this S goes from U to F. No, it's a local F-valued function. And you see, if before we thought at every point the section sigma attaches to every point in the base manifold an F, an element in F, well, the same does the S. It only does so locally, and it must do so locally, okay? It's the local representation. If you think of the sigma as a section, say, in the tangent bundle, if the associated bundle was the tangent bundle and the principal bundle the frame bundle, for instance, this familiar example, then this is just the local representation of a vector field as saying to every point in the base manifold, in some patch in the base manifold, you attach a vector, a tangent vector, right? And it's this guy that's being derived. And now this left-hand side here, we can also give it a name. We call this nabla sub t. Now, it's not the sub t of the sigma, because that was our idea from the right-hand side using the sigma. Instead, now we use the local version of sigma, but on the left-hand side, it's the little s. So in total, or in summary, with these names, we have nabla sub t on S is ds applied to t plus omega u phi acting on the S. And the t is eaten here, of course, of t. And this is, of course, precisely the formula you know for an f-valued covariant derivative, for the covariant derivative of an f-valued function. You just take the naive derivative of the function, the partial derivative, okay, and you dot into it the t. Well, this is what this does. ds of t is t alpha del alpha s in local coordinates on the base manifold. These are the connection coefficients. One index, one of the lower indices of the connection coefficients is filled with the vector in whose direction you derive. And then there are two indices left on this guy. These are the Lie algebra indices, and they act on the vector valued thing. Okay? So this is the covariant derivative you know, but you now understand how these connection coefficients that precisely appear in the covariant derivative, how they originally come, here's the Young-Mills field, but you know it's by choice of this section, how they come from the connection 1 form up there. And it's easily seen that this guy satisfies all the properties we wanted for this nabla. Again, it's only that it doesn't act on the sigma. The sigma is made into a phi up there, and the phi is pulled down to an S on the base manifold. But then it's a function on the base manifold, but it's f-valued. And that's the naive idea of a vector field. At every point, I give you a vector, but that only works locally. It only works globally if the phi section is a global section. But that can only work if the principal bundle is a trivial bundle. Then it's the same thing. Then you could also write the section over there as a global function. Okay? So you see that by the construction, we're forced. We can't do it global. No? We cannot define a global function S whose covariant derivative we write down. This is always local, but so are these connection coefficients here. So in fact, that the connection coefficients you have here, that they're only valid locally, that also forces us to make this only locally. Okay, that's it. So that's the covariant derivative in all its glory. And now I want to point out one important bit, and that is in everything we did here, we can do as we wish, and we can choose the omega as we want to have it. Okay, the connection 1 form. But there is another choice we can make. We can make the choice of what this left action is, right? Well, in order to have this covariant derivative, because of this action of the Lie algebra on here, it needs to be a linear action, a linear left action on a vector space. But we can choose two things. We can choose the connection 1 form, and quite independently, we can choose, even for a fixed vector space, what exactly is the left action. So now let me make a comment to the quantum mechanics. And this is the secret why, so apparently Christina told me that the literature says that in 2 dimensions, so what we can calculate, in 2 dimensions, you cannot write quantum mechanics in polar coordinates, but in 3 dimensions you can. Well, what is the fact is that in 2 dimensions, you need to choose this guy slightly less non-trivial. You need to absorb a factor of 2 that appears here, or a factor of 2. You need to absorb it into this action. And if in the next lecture we're going to discuss the quantum mechanics, you'll see there will be an extra factor coming up in front of a connection coefficient, in front of a Young-Mills field, which cannot be absorbed into Young-Mills field, because the Young-Mills field has this distinctive transformation behavior. You remember that a Young-Mills field transforms with this extra term. Well, if it's a matrix field, transforms like this. Under a gauge transformation. Now, if you took twice the Young-Mills field, also this term would get a factor of 2. But it doesn't, it cannot, then it's no longer a connection. So a multiple of a connection is not a connection. You know that the difference between two connections is a connection, that's still true here. It's also true that the arithmetic mean of several connections is a connection, because whatever their sum is, you divide by the total number, you produce a factor of 1 here. But if from some application you come up and you have a 2 here, you cannot absorb it into here for this reason, but you can absorb it into here. Because if something acts somehow linearly, then acting twice is still the same thing. Well, not the same thing, but it's another linear action. Okay, so we'll see an application of this next time when we discuss quantum mechanics on curved spaces.